So it is my privilege to introduce Professor Sugata Gangopadhyay. Professor Sugata Gangopadhyay is from Computer Science Department of IIT Roorkee, and he is expert in cryptography. Today he will uh, give his lecture on cipher text. So I would like to ask Gangopadhyay sir to kindly start his presentation and bless us.
Um, Hello. So, first of all, very good afternoon to you all, and I thank you for having me uh, here to give a talk. So, as I see that it is a 5-day AICTE training and learning faculty development program on cyber crime and computer security. So these are I trust that you had a good time during these 5 days, and uh, and you have learned many things and also refreshed many things definitely. So today what I will be talking about is a very specific area of computer security, and it is related to cryptanalysis. So whenever someone designs a cipher, then that cipher has to be analyzed, and its security have to be uh, bounds have to be clearly uh, characterized. So this is something that we keep on doing, and this is a very slow area. So because in some areas there are results, and one after another there are results, but this is not a area like that. I mean, it takes a lot of time to design attacks, and if you are talking about attacking the standards that are accepted by the standardizing agencies, and then it is a very difficult problem. So probably in once in 20 years, one really uh, gets an attack which is attacking the standard. Now, at this point, I'll like to share some of my thoughts and some of my experience while working on areas like this. So what I have always found is that I mean, uh, like the point is that the good results, the big results, come uh, 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 very rarely. But those results will come only if someone keeps on working on on those areas, and someone keeps on uh, I mean teaching, someone keeps on working on small student projects and like that. If we do not do that, we are surely not going to get very good results, and of course even after doing all that we may not get very good results. So because after all there are very few standards, and so how can, and those standards are usually evaluated very well. So how will we able to able to attack just like that? It doesn't happen like that. Now I will be talking about this cipher, this particular attack today, and you will see that this attack is uh, well, after uh, studying this, some people may find that this attack is very easy, very obvious. So the question I'm writing uh, within quotes, easy. Is it true? So this is my question. Now I am I am asking this question because I am very afraid of this word easy because nothing is easy. So uh, we have to be careful. We have to give everything its own respect. Another thing is that everything is easy if you are told what to do. So, well, so that is one point. There is another point over here, is that well, I'm forgetting, so I will tell that when I get time. So I remember that. So first of all, I mean, like, some people may say that what I am saying is easy. Some people will say what I am saying is difficult. But I mean, nothing is difficult, nothing is easy. Yeah, and then another point that I want to mention here, that is my observation in life, that uh, there is no hero. What does it mean? That we have a tendency of trying to search for heroes in everywhere. I mean, like, someone, like, we think only the people, exceptional people, will do exceptional work. Now, I personally don't believe this. What I feel is that people who do good work, they are people who are doing work in 10 to 5 basis every day, consistently and honestly. And if you do that, and if you are able to develop a technical and academic culture, then from from that culture, outstanding people uh, emerge. So outstanding people don't emerge out of nowhere, and in some sense there is no concept of outstanding people. So if you look at that, how someone is someone is doing exceptional work, if you check that, you will see that the people who have done exceptional work, they have been supported by exceptional technical and academic and culture. So development of that culture, and that means that development of universities, very honest and thorough culture in universities, colleges, everything, way down to schools, that is very important. So this is something, since we are all teachers, we should keep in mind. When we give someone prize for doing something, that is actually a requirement that we require to recognize someone. That is our requirement. The point is that there is no exceptional person, so to say. Everything is a collective effort. For example, whatever our country has done or not done, that is a collective effort. In our country, in spite of becoming, despite not being mm, a very rich country, we are not wealthy country. I mean, like, people, uh, but still, if you see that, if you see our achievements, you will see that we have done a lot of achievement. Now, why we have done that? We have done that because we have got a sound educational culture. And suppose we don't have that, then one or two great people are not going to keep that culture going. So this is something that I wanted to share with you. I mean, this is what I always keep in mind, or I always believe. Now let us go to the topic. So I will be talking about time memory data trade-off attack, time memory trade-off attack. Now the question is, what is that? Are you able to see when I am writing something on the screen? Hello, Harsh, Professor Harsh.
Yes, sir.
Are you able to see whatever I am writing on the screen? Hello.
Yes, sir.
Yes. Okay. Wonderful. All right. So we will be talking about symmetric ciphers. So we start from symmetric ciphers. Now, a symmetric cipher, if we look at the definition, so you will see that we say that a cipher is characterized completely by 5 sets. So the first set is a set of plain texts. So this is the symbols by which people write the messages that they want to send. This is the set of ciphertext. So these are the symbols in which the encrypted message is written, and these are the keys. And this is an encryption function. So encryption function is dependent on both the plain text and key, and to produce a ciphertext. Now we must have this property, that is, if I fix a key k, suppose k is a fixed key, then if we have if we take a decryption function, and then suppose I take the encryption of x by k and decrypt by using the decryption key, using the key k, then I must get x. So this is something must happen with encryption functions. So I am talking about only symmetric ciphers. Now after that, but one question that we ask, that after all, what are the plain texts? Now if you look at a book, in the beginning the book will say that, look, plain texts are like this. So if you take the alphabet A, consisting of A, B, C, D, and so on up to Z, and I will encode them in this way. So I will encode them by numbers, A going to 0, B going to 1, C going to 2, and after all Z going to 25. So I will encode them like this, and I will then combine them and all that. So that is a standard way of saying that in the book, first few chapters of the book, you will say that they do like this. So in that case, the plain text space becomes, what happened? Oh, it moved forward. So yes, in that, then the plain text text becomes something like 0 to 25. But in reality, it is not so. So in reality, this usually we will be encoding our messages into binary strings. So ultimately, our messages will be some kind of binary strings like this, something like that, and then broken up into blocks. So probably they will be broken up into blocks of 64 bits. So that is a kind of situation we have usually. Now in this case, so plain text space will be, what we can do is that when we have a message, we may consider that message to be a finite string of 0, 1, and we will be then cutting down the message into pieces, and so like this, and we can say that each piece is a string of length n. So this is a very standard way of doing that. So it's a string of length n. So this is if you take xi. So each of them are n-bit strings, and you can write that for any message. Only probably you will have a problem at the last bit, last segment. So that we can do something like padding, some kind of padding or something we can do. And therefore, what we will be saying is that my messages are consist of blocks of length n. So okay, we assume, or I should not say assume, that messages are made up of n-bit segments. So that's all. These segments are called blocks. So that is something that we assume. Now, the ciphering when we consider block ciphers, in a block cipher, the ciphering is done by using a key, picking a key from the key space, and then we apply that on a message, and we get a message block, and we get a cipher text block back. So this is, I will come to the picture of a block cipher, a very top level picture of a block cipher. So a block cipher is like this. So, so what we are doing, we are first taking a message, splitting that message into consecutive blocks of certain length, and this length typically may is 32 or 64 or 128, something like that. So that is important. And then we take a key. And so from a from the point of view of mathematics, we will say that a block cipher is a function from the plaintext space, which I am writing as f2 to the power n. Here, when I write f2, f2 is the set 0, 1. So if I write f2 to the power n, so it is a set 0, 1 to the power n, and the key space, that is f2 to the power m, and to the ciphertext space f2 to the power n. So this is the plaintext space, this is the key space, and this is the ciphertext space. So this is how we may write the block cipher. So it is like this. Now, what are the well-known block ciphers? The most well-known block cipher is data encryption standard. This data encryption function standard. In short, it is called DES. And another well-known block cipher is advanced encryption standard. That is called AES. Now, these are very important ciphers because by it is almost by law that any encryption has to be done by using these ciphers when I'm transmitting messages over the internet. So initially, data encryption standard was proposed in 1976, and it lasted at least up to year 2000, 2002. And in 2002, advanced encryption standard was adopted, and now it is the standard. So we are talking about the encryption standards. So both of these are block ciphers. Now, well, we will move on to see what is there in next. So I'm not talking about the details of the structures of DES and some other structures right now. I will go to the attack part. We come here. Just give me 1 minute. I'll continue the attack part. All right. So now we are in a situation where I have a sender. Let us call the sender Alice. And Alice has an encryptor, an encryption machine, and well, it is a symmetric I'm talking about symmetric ciphers, and particularly block cipher. So suppose Alice has a block cipher and we have a key. So there is a key source. So from the key space, key has been chosen and it is used for this cipher, and this key must be sent secretly to Bob, to the decryptor, and there is a channel over here that is a public channel. This is the insecure channel, and the message must go, the encrypted message must go through this insecure channel to the decryptor, who will decrypt and give it to Bob, and key must be known to both the people. So adversary Oscar is not going to know the key, so that is for certain. Now Oscar's role is to try to find the key. Now the point is that we now ask what kind of access we are giving to Oscar. So if the attack model is ciphertext only, then Oscar only has access to whatever Alice is transmitting over the channel and nothing else. So this is the insecure channel. All right. So Oscar knows that and nothing else. But in realistic situations, Oscar has access to much more. Now you will be surprised that our adversaries are more powerful than we would like them to be, or more. Our adversaries definitely are going to have more data than we are comfortable with. Now, more data for our comfort. So there is a good chance that Oscar might be having several plaintext ciphertext pairs. There's a good chance of that. And if this attack is happening under the assumption that Oscar has a access over a large number of plaintext ciphertext pairs, although he doesn't know the key, then this attack is said to be a known plaintext attack. But in reality, Oscar might have more power. It is true. I am not saying anything hypothetical. So that is called a chosen plaintext attack. And in this attack, at least for some time, Oscar has access to the encrypting machine. At least for a particular period of time, Oscar has access to the encrypting machine, encrypting machine. All right. Now, this is possible. Why it is possible, I am not talking about. So if you are talking about computer security, cyber crimes, and all that, now these are the issues. And if you go into the actual real world situations, you will find that more often than not, our adversaries have more power than we would like them to have. So this is a valid model. So I'm not going into chosen ciphertext attack, because I will not be using chosen ciphertext attack anyway. So I go to the next slide. So this is a particular attack that I would like to talk about in detail and show that how a realistic attack can be proposed by from this attack. which is usually called not an attack. So if you are looking at any, just one moment. আচ্ছা আমি বলে দিচ্ছি। Hello. All right. Okay. So, can you hear me? Hello. Hello. Can you hear me? Hello. Are you able to hear me?
Yes, sir, you are audible. Please
Audible.
continue,
Hello.
sir.
Okay, okay, wonderful. Actually, what happens? See, I am sitting in a room. There is no one. It is a closed room. All right. And I'm talking. और माने मुझे लगता है जो क्या हो रहा है कोई सुन रहा है नहीं ऐसे ही मैं बात कर रहा हूँ ठीक है आप मुझे बस 1 मिनट टाइम दे दीजिए ठीक है ना मैं आ रहा हूँ मैं कंटिन्यू करूंगा इसको Hello. Yes. Hello. Yeah, I'm back. Okay. So let us start. Huh? So the point is that what is exhaustive search attack? Like exhaustive search attacks tells us that if you can run over all the possible keys, then you can decrypt. I mean, you can attack a cipher. Then we will say that okay. I mean, like usually in a book, people will say it is not an attack. So like let us ask a question here: is it an attack? Is it an attack? All right. Now, the answer to this question is the obvious answer is no, but there is also the answer yes. Now, I will explain to you why both the answers are correct here. The reason is that the first question that one will ask that what are the assumptions under which we are proposing the exhaustive search attack. Suppose we are talking about a block cipher and suppose we are saying that it is under the assumption of chosen plain text attack, then whenever the cipher is running in the online phase, I can always plug in an input of my choice. I can always do that. If I have that power, then what I can do, I can split. What I can do is that I can split my computation into two parts. I can say that I will do pre-computation. That means that I have the function E, and because of Kirchhoff's principle, Kirchhoff's principle, I know that I know that I must have the access to all the designs of the cipher, all the design details of the cipher, and therefore, see what I will be doing is I will create. I know this function, And I have chosen one X0 because I know that ultimately I am going for a chosen ciphertext attack. Chosen plain text attack. So I will be doing that. So I know that. So I have chosen this. And then just take all the keys here and plug in the keys one by one and create this table. So I create this table and then sort this table. So create this table, create, and then sort this table. Sort. You have to sort it. This table. So this is a pre-computation. Now, suppose I have got a 64-bit cipher, then I will need a pre-computation of 2 to the power 64. Now, 2 to the power 64 is a large number. Our usual workstations can do up to 2 to the power 40. Probably I can have a very fast machine. I mean, if you have a usual 1000 many such workstations, then you can scale up to 2 to the power 50. Then also I need 2 to the power 14 such machines, but still it may be scalable, but it might take few years to do that. So I do that for few years and create this table. But after that, in the online phase, what I will be doing is to plug in this plain text, get this thing out, and then take this and search in this table. If I get a hit somewhere here, let us say, if I get a hit, then automatically I have the so suppose I get this. So suppose y0 is this, then I know that the key is here. So in the online phase, I don't have to kind of do much work. I will just have to search a sorted table. So that is exhaustive search attack. Here we see that we have a situation like this, that our situation is this: we have a pre-computation of 2 to the power n that we cannot do anything about. This is huge, but it is one time. This is a one-time pre-computation, and after that we need memory of this size. But when running time complexity in the online phase, that is the most important thing. So there I have got just order of m. This m is typically 64 or 128. So it is very small. So that is the exhaustive search attack. On the other, so if I write, see, I write memory as capital M. If I write capital M, and so capital M is 2 to the power M essentially, and I'm not writing order sign, but remember that I mean order. So, and this is 1. On the other hand, we have another observation that I could just do this computation in the online phase. That is, when I'm put x0, and then I just keep on using x0 and different keys and just check all those keys and see where I get a hit. If I do that, then I will need time equal to 2 to the power m, because I have to go in the online phase itself. I have to go 2 to the power n times. I have to do a process that is, in the worst case, it is 2 to the power m. But I don't need memory. I mean, memory is just a very small number of bits, maybe some m bits or twice m bits and like that. So I don't need memory. So I have got two extremes here. So see, so if you can think of this as a curve, Then I have got T here and M here. So either I have got T equal to 2 to the power M. So this is T equal to 2 to the power M, 2 to the power M 0. So this T equal to 2 to the power M, or it is M equal to 2 to the power M. So it is 0 2 to the power M. So I have got two extreme situations here, that I have got, I should not be saying 0 really, let's say it's 1. So it's 1. So it's not 0 0, but it is 1. Let us say this thing, let us say it is 1. So so this is not a right way of representing this thing. So I think I can do better. Let us see. I think I can do better. So I think best way is a straight line. So why a straight line? So what it will be like? So no, not a straight line. So let us try to think. I mean, like how to represent this. If I am plotting t in this direction, then 2 to the power m t equal to 1, t equal to 1, and so I have got t equal to 1, and this is 2 to the power m is 2 to the power m, this is 1, and so it is t equal to 1 and m equal to 2 to the power m, and whereas the other side is m equal to 1, so m is 1 over here, and t equal to 2 to the power m. So it's like this. So there are 2 points, extreme points that I get. So it is like this. So these are the 2 points where I'll be which are the possible complexities. Now so after the acceptance of data encryption standard in 1976, Martin Hellman proposed a trade-off between time and memory to attack DES. This is very important, and Martin Hellman published this result in IEEE Transactions of Information Theory in 1980. So this is what it is. It's IEEE, a cryptanalytic time memory trade-off attack. Trade-off IEEE Transactions on Information Theory 1980 is by Martin Hellman. And this is the same Hellman as the Diffie-Hellman public key protocol, Diffie-Hellman public key system. So it's the same Hellman. So I will like to discuss how this this approach goes, and how it is essentially a kind of exhaustive search, and that will, I'll just try to explain that in next 10 minutes and stop after that. So Hellman's approach is like this, that first of all there is an assumption, and if it is not correct for a for a cipher, then we will have to find a way to manage that. There are ways to manage that, but now let us assume this for the time being, that p, k, c all are equal to f2 to the power n. So p equal to k equal to c are equal to f2 to the power n. In other words, is 0 1 to the power n. So all of them are collection of n bit strings, and I fix a chosen plain text. This is the plain text of my choice. All right. And then what I do is that from the key space, that's also a set of all NB strings, one NB string. I choose something in random, something at random, and plug in to E. This is same as this. I get something. So what I'm doing is that I'm fixing this x0, so I can as well say that f. So this function is f of x10, which is essentially f of x0, x10. So this is a function like this, and let us say this output is x11. And so I get this x11, and then x11 goes into E. Same input, I get x12. So I have written down some symbols over here. So once I have this, then I can build a table. All right, so what I do is my f is something that I do like this. Now, so then I pick a point at random and then keep on applying it for t times. Now, when I come to this point, you will definitely ask me that what is the value of t? I will tell you that that is what I have to decide. So let us keep it at t. So that's at t times. I'll do that. So after that, I leave it and choose another thing at random, another the string, binary string of length n at random, and then I again do this. And I keep on doing this capital M times. And you'll ask me what is the value of M. Now, ideally, what I will do after this is that I will keep this portion and forget this portion. So that's also something I have to do. And I construct something called a TMTO matrix. So this is a TMTO matrix. All right. Now, let us go this step where I am kind of not created the matrix really, but I have more or less a table. The only thing is that I have to forget this. So let me see how to forget this. So let us kind of try to remove this portion somehow. If I do this, will I be able to forget this? Yes, I am forgetting this. I have forgotten this. I have also forgotten this. All right, so this is forgotten. And then I will be forgetting more things. What I will do, so I will forget this portion. Forget. So what is M and T, I will tell later. So now let me forget this portion. So I have forgotten this portion. So when I'm doing pre-computation, I will store only this column, and this column, and nothing else. And in this process, my memory will reduce, memory requirement will reduce. So when I'm preparing this pre-processing table, I do not have to keep all the intermediate values. I just don't keep, I just get the last value. So I essentially keep the second value, the value that I get after applying f once, and after that I apply ft minus 1 times, and I go to the last value and I keep that, and I keep on doing that. So initially, if I have to store this matrix, so if I have to store this matrix, the totality, I need a memory of size mt. But what I claim is that if I forget this, then my memory requirement is only m, because I will have to only store these m pointers and a very small amount of bits. So if I am talking about 64-bit keys, so I have to only store 128 bits, and so it will be 120m, 128m, and that's as good as m in the order notation. So that is the kind of memory that I require. So that this whole factor of t vanishes from my expression. So I have got less memory, and then how will I recover the keys? Now let us see how to recover the keys. For that, I will use this table and I will remove whatever I have already written. All right. So let us see. Yes, so all right. So what I will do is I'll go back to my cipher and kind of remember that ultimately I can choose my plain text to get a cipher text x0. Now I have forgotten this part of the table. So again, let me kind of forget this. I've forgotten this part of the table. I can only search for y0 over here, and I will search it, and suppose I get this thing equal to y0, but then I know that if I remember this portion, had I remembered this portion, this variable is x2 t minus 1 is my key, because x2 t minus 1 is giving me this as output when x0 is fixed input. Now how to find x2 t minus 1? Can I find it or not? Because this portion is already gone. I've forgotten that. Now to do that, I'll say that no, I think there is something I can do. I will take this thing and evaluate f over this t minus 2 times. So I have a situation like this. I have x21, x22, x23, and so on up to x2 t minus 3, x2 t minus 2, okay, x2 t minus 3, x2 t minus 2, x2 t minus 1, and x2 t. So I need this one, x2 t minus 1, and because that gives me this. Therefore, I'll start from here, and altogether there are t minus 1 operations of t, so I have to do t minus 2 operations. So if I calculate f2, wait a moment. If I apply f t minus 2 times over x21, I will get x2 t minus 1. And that is what I need. So I will have to do a computation of amount t. So I have to go 3 steps. I have to apply f t many times. So what happens here is that we see that m is reduced to small m and t is reduced to t. So we have achieved a situation where we can at least say I require less time. Now the point is that, of course, we will argue that all the keys are not here. So suppose I don't find y0 over here, then what should I do? Then what Hellman says, that apply f over y0. So instead of this, apply f over y0 and search for that. If you get a hit, suppose here, that means not this one, but the previous to that is the key. So if I get a hit here, then this is not the key, but previous to that is the key. So again, keep on going from here. In that case, ft2 minus 3 of x21 give x2 t minus 2, and that is my key. So that is how Hellman tells us to do. Now, then what will happen? So if I'm able to build a matrix which is which covers all the keys, so where mt equal to capital N, which is equal to 2 to the power n, if I can do that, then all the keys will be covered, but that is not possible. So what we know here is this: there is a result like this. Oh, I don't know where I have written that result. Oh, yeah, here. So what the result says is that in this randomized process, if we start generating keys, then we will get distinct keys as long as mt square is equal to n. Therefore, mt is equal to n by t. Now, this number is important. That means that at least when I do this, I have to keep this in mind that mt square has to be equal to 2n. That is the total number of keys, and I am getting mt equal to n by t. So that is tth part of that. I mean, like a fraction of 1 by t. So n by t. So in this process, I can cover 1/10 of all the keys. So that is, I have to keep in mind. So if I do this process, my chance of success is 1 by t. Now, suppose t is 2 to the power 10, then my chance of success is 2 to the power minus 10, which is 1 by 1024, which is actually not bad. But Hellman doesn't stop here. He gives us a technique in this paper, that this IEEE paper in 1980. So he gives us a technique to generate all the keys. So that is a specialized technique. So I am not talking about that right now, but it is true there is a technique of that, and that from that we get an algorithm by using which we can cover all the keys by a certain process. So as a result of this, Hellman could propose the first attack on DES. So in 1980. So using this algorithm, using this technique, Hellman proposed the first attack on DES in 1980. That is just 4 years after DES was adopted as a standard. All right. So with this, I will end my talk today, and I have got more information in these slides. So if you like, I'll be happy to share my slides, and if you go through the slides, I'll be happy to discuss aspects of time memory trade-off. So let me stop here, and thank you very much. Questions, please.
Participants, if you have any question, kindly ask. You may also write in the chat box. Thank you, sir.
Okay,
I
not a
think
problem. That's absolutely all
uh,
right. So it was good to give a lecture in this remote mode, and I hope that I will have chance to visit your institute
sure,
sometime when things become normal. And so, okay then, bye bye.
Thank you, sir.
I will
Thank you,
sign
sir.
off then. Okay.
We will invite you, sir. Kindly share your PPTs. So I will
Yes,
give it
I will
to.
share that after some time. I'll kind of send it off to you.
Thank you, sir. It was
Okay.
very
Okay. Bye.
informative and excellent lecture, and participants
Thank you very
learned
much.
lots of things. Thank you, sir.
Thank you
Thank
very
you.
much. Thank you. Bye bye. Bye.
So, dear participants, uh, so now after 2 to 3 minutes, I will share the link of assessment test. So kindly stay on.